Hello everyone, my name is Nicoya, and these are my lights. So let's talk about these lights for a minute. They are an LED light, despite looking like fluorescence. They just have a little LED strip that goes through these tubes. And they have a motion sensor on them, which I have disconnected temporarily. We'll get into that in a bit. So that, presumably when you walk underneath them, they turn on, which is nice because they just, plug into a regular outlet, 2-prong. So they're expecting you to put this in the cases where you might not necessarily have a switch controlling the lights. So they're great for, a closet, a shed, garage like I have them in. As long as you're not in there long enough for the lights to turn off, or your space is small enough that the beam pattern of the infrared detector is continuously detecting you. What I've found is that my garage is, of course, much larger than what this single beam pattern per light will detect. And so, if I'm over on this side of the garage and this light is over on the other side of the garage and I'm standing around for like 10 minutes working on something, this light over here is going to turn off, and that's kind of annoying because I'm still making use of its light, or at least I would be if it were actually still shining. So I want to make some changes to this light. I want to theoretically still keep the infrared going, but I want to add an override to it with a pull chain switch. And so this is just a standard, pull on, pull off switch. It was cheap on Amazon, cheap enough that they limited you to only buying 6 at a time, which is okay because I have 6 lights, so that's cool. Now, given that this is hooked up to an infrared motion detector, what we can't do is we can't just take this wire, put it in the 120 volt line input, and expect to be able to pull the chain to turn the light on and have it stay on forever, because the infrared detector is going to time out after a while and turn it back off again. And if we pull it again, the light's just going to go off and stay off, and that's not really what I want. On the other hand, because this is an LED, this isn't a, it's not an incandescent bulb that runs directly off 120 volts. It's not a fluorescent where this is literally just a ballast or something. I could, bypass this directly and send the 120 volts to the ballast to have the lights going on all the time. We have to be a little bit more creative here, and so that's what this video is going to be about, is looking at this controller board, this power supply board, and saying, okay, you know what, this connector here is what was telling this board to come on. How do we inject our switch in there such that, in one state we say the light should stay on all the time, and in the other state we say that the light is going to time out naturally based on the infrared. So how do we do that? To figure that out, we have to figure out a little bit about how this circuit actually works. So I want to dedicate the next part of this video to sort of addressing the concept of, like, you come into a project with an unknown circuit, you want to modify it. Like, where do you even start? Like, there's components on the back, there's components on the front, there's wires coming out of here all over the place. There's, lethal voltages everywhere here, by the way, so for goodness sakes, leave this thing unplugged when you're in here. Nothing is isolated. Where do you start making sense of this kind of circuit? So I'm going to bring you around to a different angle so you can get a better look at this board, and we'll see how I approach that. Okay, so we got a pretty good picture of the back of the board here. The first thing we want to do when we see a board like this is sort of identify our landmarks here, right? So on the front side here, we have a wire that's going to our LEDs, and so clearly this is the output that's driving the LED. And hooked up in parallel with that is a big capacitor. It's like literally in parallel. It's like the same solder blobs. And then over on this side of the board, can't really flip it around the other way, but like we see a bunch of passives here. There's class X capacitors. There's an MOV over here. I can't really show you, but right under here is a common mode choke, and then we have a full wave rectifier here. And so basically everything on this side of the board is kind of just, power line conditioning, dealing with EMI, that kind of stuff. Like, it's common to basically any circuit you'll find. It's not really that interesting in terms of figuring out how this board works. Up here we have a chip with a lot of pins on it, so theoretically that's going to be the brains of our operation here. We can also see we have a 3-pin device here. One of the pins is actually the tab on the back here. So, presumably this is going to be some sort of transistor-like device. There's a two lead device here. That's presumably going to be a diode. these pins here are connected to the backside on this large inductor. And so when we're looking at this, we're sort of thinking, okay, this is driving LEDs. It's probably going to be a constant current supply where we don't have any sort of step down transformer here. So this is going to be a constant current buck supply. So that's sort of our first thought there. And so if we think about, what does the topology of that look like? Well, on the high side, we'll have a MOSFET, and that MOSFET will feed current through our inductor and out through our circuit and then back to the negative side. We'll also have a diode here, which when the MOSFET switches off, that allows the current to keep going as the magnetic field starts collapsing, and we'll get into this more a little bit later. And so now we can sort of see, this MOSFET, well, that pin goes over to this chip here, so that's probably the gate. And then, your source and your drain and everything are hooked up here, whether it's P channel or N channel, who knows? We'll have to look at the spec sheet. Hint, it's always N channel. So we can see the output is going to be this, lake here, and then there's some components here, whatever they're doing, I don't know. There's a missing component there, we'll get to that in a second. And there's some other passives. There's some stuff up here that's kind of a mystery, is sort of off to the side. But we got our basic layout here, right? We got our inductor, we got our diode, we got our MOSFET, and we have our regulator controller. So that's sort of our first orientation here, right? So now what we can do is we can zoom in really close to this chip here and try to read a part number off it. And I'm not going to try to zoom in with my camera here because it'll probably just take forever and you won't be able to see anything anyways. I'll tell you it is a KP106, which is Kiwi something Corporation of China, and they have a spec sheet online for this chip, and it is terrible, but it does contain a example application circuit, which is partly unlabeled, but it's fine. It'll be enough to sort of start us in. And so I'm going to actually put a picture of that on screen right now. Hopefully I remember to do that in editing. So you got your regulator, you got your inductor, you got your diode, and you have your load circuit represented by the LEDs here. So we have our basic orientation now. So that's sort of how I approach this circuit from starting. Now we still have some mysteries here, right? Because we have our entire IR board, and it's hooked up to these 3 leads down the bottom. And so, luckily these 3 leads are labeled. On the other side, I can't really show it, but they're also labeled on this side here. And so we have, let's see, you probably can't read that, but from top to bottom, right by my thumbnail there, it says PWM, ground, and VN. And so we have some idea here of what this is doing, right? We have a mystery chip of some kind. I don't know what that does, theoretically. We have something over here that's doing something from the VN, because this is a dual-sided board, and you can see there's the vias go through from the VN over to here, and then that ends up coming back up to these vias in here. And so this is probably some sort of power thing. This large lake over here, this side of the board, is probably going to be, some sort of ground plane. And we can see some vias through here that go to the top side, and it's just, a large ground plane here. So that's obviously going to be our board ground. So we're sort of getting, a little bit oriented. We can look up the part number of this component online, and you probably can't see it, but it says PIR, and it says, what does it say again? AV612 or AW612. Anyways, it's a very common PIR. It has a very good data sheet, and so you can actually look it up. And if you actually compare what's on the back here to what's on the spec sheet, you see that pin 1 here is your power, pin 2 is our output, pin 6 is ground, and the other 4 pins are just setting some various configuration parameters on it for, what's its sensitivity, how long is its timeout, etc., etc. So we basically got this board sussed out. We got a regulator, we got a mystery chip, we got our PIR, we got some components that are just setting some values. And so now we can say, well, first of all, what's this mystery chip? Because this mystery chip is standing in between our PWM output and whatever our PIR is putting out. And as it turns out, this is a delay circuit. So basically what it does is it takes a pulse in and it stretches it out to 10 minutes and then it turns it off. And so I guess a one-shot resettable timer or something like that. It's basically, a very, very specific circuit just for this board. I believe that they probably use this chip so that the output would come in at a high state rather than this PIR sensor. Probably when it first powers on, it doesn't immediately go into an active state or something like that, and so that's probably why they put that chip on there. So that's the idea of this board, right? So now we sort of got this sussed out, and we sort of have some idea of what's going on in this board. But the question is, how do we change its function? And how do we say, you know what, I want this to stay on, or you know what, I want this to, instead of turning off when the timer times out, I want this to go dim instead, right? So how do we do that? Well, if you look at the board here and you say, oh, that says PWM on it, and you think to yourself, well, I'm going to try to send a square wave to that input. Well, I tried it and it doesn't work. And to find out why, let's look at an actual circuit diagram that I reverse engineered off this. All right, so here we are in KiCad, and this is the schematic that I reverse engineered from the driver board of my light. So I tried to orient this schematic in the same rough layout as the board itself, so we can, things line up the same way that we were looking at them. So over here on the right side, we can see that we have all of our input filtering from the line in here. We have our fuse, we have our MOV, we have our class X capacitors, we have our common mode choke. There's a couple more filter capacitors here. This one's sort of a main filter capacitor across the lines. We have an inductor. This is another capacitor making a low-pass filter here. So all of this basically we can ignore. This is just giving us 160 volts, whatever DC, into our circuit. What we care about is all the stuff on this side, and mostly just the stuff in this quadrant here, right? Because this is where our board connects from our PIR board. So we have our PWM, we have our ground, and we have our VN here. And so, VN, this is being supplied through some magic. And if you look at, this bridge up here, you can sort of figure it out. We'll get to that in a sec. We have a little capacitor to keep the ripple out of the supply there. And, our ground is coming back to source of this MOSFET here. So the important part of this, of course, is, quote unquote PWM line that's coming in here. So this comes in, just loops up around. You have this pull down resistor going to, the quote unquote ground of the PWM board. And then it goes over to the gate of the MOSFET. And so you say, okay, well, when this PWM line is high compared to the quote unquote ground of the PIR board, then this MOSFET conducts. So what does that mean? Well, that means that from this, our main switching MOSFET here that's controlling our inductor, the power comes in on our HV line here, our HV plus line, comes down through this MOSFET, and then it comes down, and it's going to go through this control MOSFET here, our 2312 here, and it's going to go through these three resistors here. And so these are just 1.1 ohm resistors, all three in parallel, so you got about like a third of an ohm here. And so, why do we want a third of an ohm here? Well, if we look at what else is connected to this sort of lake in here, we have the CS pin of our KP106, and thankfully we have the data sheet for this. CS means current sense, and so presumably it's going to be measuring the voltage across a resistance to figure out what the current is. And so we have our quote unquote known resistance here of 0.3 ohms. We have the current sense pin, and there's also this FB pin. This is like a feedback pin. It's basically telling us what the voltage is on the other side of all of this. And you can see it has this bridge that basically goes across our main inductor, our L3 here. And so it's basically measuring the voltage between this point in this bridge here, which is just spanning this inductor, and this point over here, which is the output of our MOSFET. And so it can tell somewhat indirectly how much current is going through this inductor, and that tells it, since it's a current controlled supply, this tells it how much current is eventually going down here through our LEDs. So that means that, obviously, when this MOSFET is conducting, we have 0.3 ohms here. And so, however many millivolts or milliamperes is going through these LEDs, you're going to have V equals IR or whatever volts across these resistors. And so this is just programmed to hold that voltage at essentially one particular pre-configured voltage. And there's like the comparison pin in here that's hooked up to this circuit that like adjusts that and does stuff. I couldn't find a good documentation on like what the expected input to this comparison pin is, and so I can only kind of hand wave around this, but in some way this controls how much voltage is expected to see there, and it's basically a fixed voltage. So we have a small resistance here, and we're expecting a fixed voltage over that, so that means we're going to get a relatively high current going through this inductor, which means we're going to have a relatively high current going through the LEDs. And again, we're talking like less than 1 amp or something here. But what's critical here is to figure out what happens when this MOSFET turns off. And so when this MOSFET turns off, then the only connection between our inductor here and our driving MOSFET is this resistor here, which is R9, which is a 10K resistor. And so now this changes the equation a lot, because remember, this is all the V equals IR stuff. So R just went up, which means that I is going way down. And so when only this resistor is in circuit, we have a much, much smaller current going through L3, because remember, this is just trying to keep a fixed voltage across, whatever quote unquote fixed resistance is between our MOSFET and our inductor, right? And so, when this resistance goes up, because we removed these 3 parallel resistors from the circuit, that means that the voltage for a given current will go up, or, since we're holding the voltage across this constant, the current's going to go down because the resistance went up. So that's how this is turning on and off. So it's sort of, I should say quote unquote off. It's never actually fully off, because we always have this sort of small leakage current going through the entire circuit. And you can actually see that when you turn the lights off afterwards. There'll be like a really, really slight glow, or turn the lights off like with this controller, obviously. There'll be like a really slight glow from the LEDs, and it won't go like 100% dark, and that's because it's still moving this tiny amount of current, through L3 and through the LEDs and, back to HV minus here. So if we want to make a modification to the circuit to say, I want this to be dimmed, then first of all, looking at this, PWM pin and thinking to myself, I'm going to put a square wave in here. Well, what's going to happen then? Well, we're going to end up with this MOSFET switching on and off really quickly. What it means essentially is that we're going to really confuse this chip, and it's going to say, I'm going to switch this MOSFET on and wait for the voltage across this resistance to rise to whatever many millivolts, and then I'm going to shut this MOSFET off again and wait for the voltage to drop to so many millivolts, because the current's coming through the diode and just sort of looping in a circle, and the magnetic field that's storing the energy in our inductor here is winding down. If we just switch this mid-cycle, we do that once, it gets a little confused, it recovers, and it goes back to business as usual. If we do that like a bunch of times a second, then this thing's going to be chasing its tail trying to keep up with us. So let's say we pick 150 hertz or something like that. We're bouncing this up and down at 150 hertz. This thing's this is bouncing up and down at 150 hertz. The voltage between here is going all kinds of crazy. This chip isn't figuring, this chip has like an integrator in it that's trying to like figure out how much current is going through L3, and we're like telling all kinds of crazy things, because it'll switch this on, and then suddenly we'll put this 10K resistance in here, and this will probably go to like frickin' 30 volts or something when we make this switch here, and it's like, oh my god, there's suddenly 30 volts here, I'm putting way too much through this, let's be crazy and shut this off because like I have an overcurrent protection or something, and then it shuts it down, and then suddenly, we switch this on again, and now instead of, showing, 30 volts across here, it's like 0.003 volts, and the integrator in here is, again, getting all confused and wondering if we're, like, accidentally short-circuited the output because something changed right in the middle of the cycle or something here, and if we're only doing this, once every 10 minutes, it recovers and it does fine. If we're doing it 150 times a second, it never recovers. And yeah, I hooked up a function generator to the PWM input because, at first I didn't bother reverse engineering the circuit. I was just like, it says PWM on the pin, so let's put in pulse width modulated signal. And oh my god, it went into this crazy flickering, blinking cycle of doom. And I was like, nope, that's not right. So the next thing I thought, it was like, I thought to myself, well, it's not clearly designed to take a square wave pulse train in here with varying duty cycle. But what would happen if I just put a voltage in here? Now remember, this is before I had gone and reverse engineered this circuit here, and so I was just trying stuff and seeing what was going to work, right? And so I had measured out that this PWM went to about 3.3 volts over the reference ground here, and so I just hooked up my bench supply, put 3.3 volts to this gate here, and the lights turned on exactly as it should. Then I turned the voltage down, and the lights actually dimmed, which was interesting. And looking at the circuit now, we can sort of see why that was working. So when we got down from the saturation voltage of this MOSFET here, it goes into its transconductance region where the voltage times GM is going to give you your drain source resistance. And so we drop the voltage a little bit, and this goes up to maybe 5 ohms or something, and light gets a little dimmer. We drop the voltage a little bit more, this goes up to 10 ohms, the light gets even dimmer, and drop it a little more, maybe it goes to 15 or 20 ohms, and eventually it just gets to the point where it's going to effectively shut off, because we're getting to the point where we're showing it a large enough resistance here that the current is driving through L3 basically goes to a negligible value, and the LEDs are no longer illuminated, right? And so I thought to myself, well, okay, maybe if I want to have this, when it turns off just dim, maybe I can pick a voltage and just say that, instead of going between 3.3 volts and ground on the input to this MOSFET, it'll just go between 3.3 and 0.6 or 1.1 or some value that looks nice. And in theory, sort of, that might kind of work, except that when you learn about MOSFETs, you think they're this magical device that you just give it a voltage and it gives you this resistance, which is determined by the GM transconductance value and everything. And then, 3 minutes later in the lesson, the professor crushes all your hopes and dreams and tells you that, in fact, that's a terrible way to do things, because, GM will vary by the temperature of the ambient circuit, and it will vary by, wildly by just where in the production run this MOSFET was generated. And I'm talking wildly volts. You might get multiple volt differences in the gate voltage required for a certain resistance across this MOSFET, just from even within the same batch of MOSFETs, just one component to the next. It's just it's just variations in the process, and it's you just absolutely can't rely on it. So that idea is kind of out. So then I thought, well, you know what? And again, this is sort of before I'd fully thought through this entire circuit and deconstructed it and reverse engineered it. I thought, you know what? Let's disconnect the LED plus line here, and we'll just, insert another MOSFET here on the output and just run a PWM through that, and the LED will, I know this is just going to blink here when I put a PWM control on it, and I'm going to have perfectly accurate 0 to 100% control on it, and life is going to be good, nothing can possibly go wrong, right? Except, of course, for the fact that this is a constant current supply. Now, it has overvoltage protection, I should mention, and so if we disconnect LED plus here and just leave it hanging, this line here, this part of the circuit, will go up quite high, but because it's sensing this voltage through this bridge here, it'll be able to say, you know what, I'm not getting any more voltage here across its sense lines, between the feedback line and the HV, or between the current sense and the FB. It has a high voltage shutdown, it's mentioned somewhere in the spec sheet, I believe. So it would just probably, raise this LED plus to, maybe 100 volts and then shut off from over voltage. It'll say you know what, you are going way out of spec here. We're not going to set fire to your LEDs. We're going to turn off. So that would be bad. The other thing that would be bad is if this goes up to 100 volts and our PWM switches on, because now we're 30 volts above what this string of LEDs is expecting, and so it's suddenly going to dump a bunch of current out of this capacitor through the string of LEDs and probably just blow them up. So that idea, not so good. So now I'm thinking like, okay, what the hell am I going to do? I can't really just, feed a voltage through this MOSFET and expect things to stay consistent. Like the temperature is going to go up 2 degrees in my garage and the lights are just going to dim or go bright or whichever way the gain changes on this MOSFET, right? Never mind that I'm going to build the same circuit, plug it into 6 of these lights, and they're all going to dim to different values. So that's terrible. And I say, well, you know what? Maybe I can put like some sort of current sensing here, and then use that as feedback for the control voltage. And too much headache. It's absolutely like not interested in doing any of this because there's a simpler way. So once I reverse engineered this, you're probably, if you have some electrical smarts too, you probably figured this out like long before I ever did. But the secret is this 10K resistor right here. This is what sets our power off, quote unquote, current through the LED string. And if I change the value of this resistor, that means that in the power off state, when this MOSFET is switched off, I will get a different amount of current going through L3 controlled by our constant current LED driver controller here. Stupid simple. So I got out my pack of resistors to try a couple values, and it turns out that about 10 ohms is a pretty decent resistance put here to get a good amount of sort of dim, kind of night light-ish light out of this when it's in its off state. And so I'm like, this is beautiful. I love this. Now, I'm not going to actually remove this 10K resistor for 2 reasons. Number one, I don't need to. I can just put 10 ohms across this, and because they're in parallel, it'll be, 9.999 whatever ohms. It's not going to make a difference. It's just a nominal value anyways. The other reason is because all of these components are glued down. They're surface mount. You don't have to glue them down, but depending on the manufacturer, some of them glue them down, some of them don't. And all of these components are glued down. So I am not going to try to chisel this off the board because I already had to do that to the MOSFET I blew up. And by the way, I blew this up because I had hooked up my power supply to the gate of this MOSFET. And because of the way I'd hooked up the leads, it was a lot easier to remove the lead from the quote-unquote ground pin than it was from the MOSFET gate, which unfortunately meant that there is a large floating voltage going directly into the gate of this MOSFET, which is unfortunate because it's kind of what you're not supposed to do to a MOSFET. So that's how I blew that up. And we're going to replace that shortly. So you'll get to see me try to solder some surface mount stuff, along with the resistor here. Anyways, where was I? Yeah, so we're going to put a 10 ohm resistor in parallel with a 10K resistor. That's going to set our current for our power off state. So that's a little bit light, not quite a completely 100% off. Because there's sometimes it's like, I want to just look out into my garage and say, did I remember to lock the door on the far side of the garage? If the lights are 100% out, I can't see shit. If they're on just a little bit, I should be able to see if it's locked or not. And granted, I could, make a project where I have some sort of like wireless detector that pages me when it detects that the door, yeah, that's a project for another day. I may do it, may not, who knows. Keep an eye on the channel for that. Anyways, that's one half of it. That is setting the dim level. The other half of it is, remember, we want to be able to put in our pull chain to override this PWM signal. Now, I measured V in here as being about 11 volts or so when the lights are on. And I say when the lights are on because that's kind of important. This little Zener divider network is kind of weird. I say that with love. It takes a supply voltage from the VDD supply here. This is basically, I think it has like an internal charge pump in here so that it can generate a gate voltage that's actually above the supply voltage here. I think that charge pump is exposed through this pin, and so you can sort of take a leakage current off of that. But it's not particularly well regulated. It's just the charge pump, right? And then the other way it works is that you have, this is going to be kind of hard to explain, but basically when this goes positive enough, this will actually go through this Zener, which is kind of high side regulating it. It's a little weird that way. Then that'll feed through here. And so that's, I think what this is doing is that's making it so it's not always drawing off the charge pump so that, this doesn't this chip doesn't brown out and is unable to like actually power this MOSFET here. But long story short, this is not a very well regulated supply. It's kind of around 11 volts, and I don't want to put 11 volts on this MOSFET because I'm not actually sure what the recommended gate voltage of this is. Needless to say, I don't want to like just put random voltages on there. And I don't have to, because remember when we looked at our PIR board, which is hooked up here, we noted that there was a linear voltage regulator on it that outputs 3.3 volts, because that's where the 3.3 volts that is getting to drive this PWM signal is. And so I'm going to do three things. Number one, I'm going to put a jumper wire from that 3.3 volt supply to our switch. I'm going to come from that switch to this PWM pin here. I'm going to put a TVS between basically this PWM pin and this ground pin. I'm actually going to hook off the bottom of this capacitor here so that I don't, accidentally cook another one of these MOSFETs, because I really don't want to have to solder more than one of these. And then I have a diode that I'm going to put in between the output of our little, timer circuit specialized IC on our PIR board. I'm going to put a diode there just so that we're not accidentally backfeeding in case it's trying to pull this low. I don't think it will. I mean, I think it's just going to use this 10K R1 to pull the gate voltage low, but I'd rather not blow up that chip in case it does try to pull it low. And so I'm going to just put a little Schottky diode in there. It's not going to affect anything in terms of like this being able to turn on, and it's going to prevent us from like trying to backfeed that chip and accidentally blowing it up. So I'm going to switch back over to my regular camera, and I'm going to try to solder in a new 2312 here. And yeah, wish me luck. All right, it is soldering time. Shit's got real when the helping hands come out. So these are our MOSFETs. I got 10 of them because they're cheap, and because I fully expect to possibly destroy one of these. I've destroyed one already, so who knows if I'm going to destroy another one. So, let's see if I can get one of these out of here. Actually, I want to put a little bit of flux on these pads. So, that will make life a little bit easier, I hope. Mostly just so this MOSFET doesn't go flying around. It'll try to stick down a little bit. I might try to pull one of these out. And of course, if I had a $10,000 pick and place machine, I'd be able to do this a lot easier, but that is not the world we live in. Alright, it is stuck to the end of my tweezers here, so that's a good sign. And I want to get this on here, like that. You'll probably have no idea what I'm doing here, but I promise you things are happening. More light on the situation, and let's see, can I see anything whatsoever? It helps if I'm actually pointing at it. There we go, now I can see stuff. Cool. Yeah, we're pretty much aligned there. Just gonna give it a little bit of a nudge. Ooh, too much of a nudge. There we go, that's perfect. So now, just need to solder this. And let's see how we did. Oh, that looks so beautiful. There's the gate. And there's the source of the ring. Whichever one is which. I get confused all the time. Alright. Going to check our work with the bino. Oh, that looks beautiful. Actually, I think the gate might need another touch. Let me just hit that once more. It's probably fine, but let's see how that looks. So now, of course I'm going to clean off the excess flux and everything, but I'll do that once I've soldered the other parts on there. Now, if I plug this in, after removing the helping hands, of course, what we should see is that when I touch this to this, that the lights come on. So, hope I don't electrocute myself. Hope I don't cause everything to fall over. So, plug this in, no smoke, that's a good sign. And if we touch this to this, we should see light, except we don't. That is no bueno. Why do we not see light? That is a good question. Did I not get the gate on? Yeah, I'm going to give the gate just a touch more solder. So I'm just going to touch a little bit of solder at the tip here. And just come in here with that blob. And make double sure. You know, it still looks suspiciously like it's not soldered, which is weird. There we go. I definitely soldered that time. Oh yeah, that's perfect. Okay, so if it doesn't work this time, I have more debugging to do. Connect this here. Hey, there we go. You can see that coming on and off. So that's what happens when we connect the PWM. I think you can sort of see me connecting that. And pull this up a little bit. So, you can't really see that anyways. Anyway, trust me, I'm connecting the PWM line back and forth. And I'm making the light happen. So that's cool. I fixed it. Next up, we have to solder, after we unplug that, we have to solder our 10 ohm resistor across this 1K resistor. So again, that's going to be fun, for some definition of fun. Also have to find the resistor because I just have a gigantic resistor kit that I have to open up and find a 10K in. So I'm going to pause you and come back when I'm ready to solder this. Yay, I found them. Here's my 10 ohm resistors. And I thought this package resistor kit would come sorted, but they were taped together in 2 bundles, but there was no order to it whatsoever. I don't know how they double check that they have all the values that they're promising in this kit, but whatever. So, time to play resistor Jenga. So we're going to take one of these resistors, pop it on top of this 10K resistor here, and then magic's going to happen. It's going to light up dimly when it's turned off instead of going completely off. I hope. Let's see. So, get one of these out of the package. Pop that out of there. Try not to lose it. A little bit of flux on here again. Make sure we get good solder flow, and also helps glue down the component while we're soldering it. So I need to flip that over like that, and then stick it to the top of this resistor and try to nudge it in place and not be a complete and utter failure at life. Hope that this doesn't stick to my soldering iron. It might, but I hope it doesn't. Let me get the helping hands back on here and help stabilize it a little bit. And a little solder on the iron, because we're going to need the extra blob on there. And we will come in from the back side. Really nice that this iron was a bit shorter, but it is what it is, I guess. Moved a little bit. I need to shove it over as it's. There we go. That should be fine. Now, a little more solder on the tip here. And solder the other side. Yeah, that looks alright. Check it with the bino, and yeah, it actually looks pretty good. Got good contact on there. Got our 10 ohm resistor there, and I'm actually going to measure the resistance across that. Let me get my meter out, and we'll make sure that from one blob of solder to the other we have 10 ohms. And we'll come in here, and 10.1. I'd say we are a winner. So now, take off the helping hands, plug this in. Hey, there we go. As we can see, probably not, I'll move you around a little bit. We have very slight light output. So we can see when it's fully on, that's what it looks like. When it's quote-unquote off, it's sort of dim. And when it's fully off, it's off. Awesome. I love it when the plan comes together. All right, next up, we need to grab our TVS, hook that across the gate so that I don't blow up this MOSFET that I just finished installing. You know what, I'm not going to show the soldering of that or the diode because that's just going to be a headache and I really want to get through this. So I'm going to come back when this is already soldered and I'll show you how it looks. Alright, so our soldering work is complete here. You can see on the back of the board I soldered red wire here to one of the unused, unpopulated pads on the 3.3 volt supply here. I don't know if you can actually see close enough to see the traces, but it comes over from the 3.3 volt supply. On the back side here, we can see that I put in a diode there on the signal line and a little bit of heat shrink over the end. So now this chip on the other side is protected in case it tries to pull that line low. It's just going to be looking into the ass end of a diode instead of trying to sync whatever current is going through our switch, this switch here. And then on the back of the board here, we have our TVS in place, as well as we have the other wire for our switch. And so all I need to do is reassemble this, and I'll poke a hole in the back here and I'll put the switch in, so it's probably coming out like right around there. So it's, you know, just in front of the where the motion detector is. And then, you know, when I switch the switch on, it's gonna not turn off anymore. And when I switch the switch off, it'll turn off when the timer time's out. And I would show you that happening, except you would just be staring at the screen for 10 minutes waiting for literally nothing to happen. And as tedious as this video probably is, I at least respect you guys enough to not put you through that. So everything still works. We can plug it in, it turns on. You know, thank goodness. Yeah, this project I say is a success. I got to do this like 6 more times. At least I don't have to, you know, replace that MOSFET 6 more times. I only blow up one of them. But you just have to play resistor Jenga, add the TVS, the diode, and the 2 leads, drill a couple holes, mount up the switch, and my project will be good to go. So I might insert like a still picture afterwards of this in place, hanging with the chain dangling down or something, or I might not. Either way, I hope you guys enjoyed the video, and I look forward to seeing you on the next one.